Welcome to 2.3 Quadratic Functions, where we learn all about the two main forms that we can put quadratic functions in, which are called general form and vertex form. The objectives today are to understand that we can write a quadratic equation or function in either one of these forms, and to convert between those two forms using either completing the square method or expansion algebra like multiplication. What is a quadratic function? Hopefully we know this by now, but a quadratic function is one of this form, ax squared plus bx plus c. Here, this is saying a, b, and c all have to be members of the real number system. So they have to be real numbers, a, b, and c. And a cannot be 0. Let's think about why not. If a was 0, we would not have an x squared term, and the x squared term is what makes a quadratic a quadratic. So a, b, and c must be real numbers, and a can't be 0. B and c can be 0, though. A quadratic would be sufficient to just be like 4x squared and not have a b or a c term. That's fine. But so you need the x squared term to make it a quadratic. Its shape, as we already know, is a parabola. We've already studied that. And the domain of any quadratic function is all real numbers from negative infinity to positive infinity. The general form of a quadratic looks just like what we've already seen. It looks just like this. F of x equals ax squared plus bx plus c. And we have those same parameters on it. A, b, and c all have to be a part of the real number system, and a cannot equal 0. So those are the parameters of it. But this is called general form. No parentheses. It looks just like a regular polynomial, term separated by plus or minus signs, depending on if a, b, and c are positive or negative. Vertex form of a quadratic does have parentheses in it and looks a little bit more complex. It looks like f of x equals a, so the a is still the lead coefficient, and then in parentheses we have x minus h, quantity squared, plus k. The a is still the lead coefficient, which is the same in both forms, and if a is positive, our parabola opens up. And then if a is negative, our parabola opens down. So a leads the way. Now h and k, we'll get more into that in the next video, but h and k are actually the vertex, which is why this is called the vertex form of a quadratic. Your book actually calls this standard form, but I've normally heard it called vertex form. But just so you know, your book calls this standard form. I like calling it vertex form because it tells us what the vertex is. All right, we have some parameters on this one too. These all have to be real numbers again. A, h, and k all have to be members of the real number system. And once again, a cannot be 0 because if a was 0, it would wipe out this squared term and we would no longer have an x squared, so it would not be a quadratic. So there you have it. We have the general and the vertex forms of a quadratic. Any quadratic equation or function could be written in either form. And now we're going to learn how we can convert between these two forms. Our first two examples will be converting from general form into vertex form. So let's recall what vertex form looks like. Remember that vertex form looks like this. So we need to have something squared, some binomial squared in it, and then plus or minus a number. We might not see an a out in front. Like if we notice in this problem, our a is actually 1. So a will again be 1 here. We won't see anything out front. But I just wanted to show you this because in order to get something to look like this perfect square here, we need to do what's called completing the square in order to make this happen. Now I can almost hear the groans from here. I'm sure you've done completing the square already, and a lot of students don't love it, but I promise it's not going to be too bad. I'm going to sort of narrate my work off to the side. So in here in this first step, it's not really a step, this is just already in general form. So I'm just going to write that it's in general form right now. The first step that we really want to do is leave some space to complete the square. We actually notice that the x squared term and the x term are both on this side, which is great. If that wasn't the case, we'd have to do some rearranging. So what we're going to do is rewrite and leave a little bit of space on both sides in order to complete that square. Now these are the two terms that are important. We're going to put a plus something right after it here. And then we still, of course, have that plus 3. So I call this step leave space for completing the square. Completing the square. Now in orange, I'm actually going to complete the square. So I'm actually going to complete the square. I'll just write complete the square. Now, how do we complete the square? Completing the square means figuring out the number that goes here so that these three terms are a perfect square trinomial, meaning we can write it in one single parentheses with something squared. I'm trying to make this happen up here. All right, the way that we do that is we take our b value. In this case, it's -8. We take half of it, then we square. So let's write down that process. CTS over here, completing the square. We're going to take half of our -8. That is -4. That's the first part of completing the square. The second part is you take that value, -4, and you square it. And that's what we add to both sides, 16. We added it to the right-hand side. That was the completing the square process. The reason we also have to add it to this side is because of this equal symbol. It's not equal unless you do the same thing to both sides. So we are manipulating an equation. We're not changing what the equation means. We have to add that same number to both sides. All right, we have successfully completed the square. Now, this right here is called a perfect square trinomial. Let's think about how this can be rewritten. I could factor this. What are two numbers that multiply to 16 that add to -8? Well, -4 and -4. So you would factor this as x minus 4, wouldn't you? However, since it's the same, we do not need to write it twice. We can simply write it one time and then square it, because squaring means multiplying something by itself. This means x minus 4 times x minus 4. That's why we have just completed this square. We've created a perfect square trinomial that can be written as something squared. So what did I just do in green? I factored the trinomial that we created. The trinomial. All right, then I'm going to bring everything else down in yellow. So we have f of x plus 16, and then equals that, plus 3 still on the end. We're really close. We're really close. I just need f of x by itself. So to do that, I'm going to subtract 16. And we'll do that in white at the end. So we have f of x equals x minus 4 quantity squared minus 13. This is vertex form. So this original function was in general form. We converted it to become in vertex form. If you were to graph this function and this function, they'd be the exact same graph. Again, we're not changing the graph, we're just changing how the equation looks. It's just in a different form. So that last thing that we did was solve for f of x. We wanted f of x by itself. Okay, in our second example, I have left the directions over here. We will just have to switch them up a little bit for like our numbers here, because these are just copied from the first example. So let me do that first. Okay, the other thing that we need to do is make sure that the x squared term is positive. So I am going to do something first just to rewrite it. So we're going to factor out that -1 to just these first two terms. And then just leave the plus 6 out there, because that is that excess piece at the end. We don't need that really. This is what we're concerned about in here and adding something on after this. All right, again, the reason I did that is because we want a positive 1a value in front of the x squared term. Okay, the next thing we need to do is leave space for completing the square. So let's do that in yellow. So I'm going to leave space on both sides of our equal sign. And I'm adding on after this x, so I'm going to leave space there. And then we still have that plus 6 out at the end. All right, so now we have to figure out, what am I adding here? How do I complete the square? Well, we have to take 1/2 of our b value. 1/2 of b. What is b? b is the number in front of our x term. It happens to be 1. So we are going to take 1/2 of 1, which is 1/2, and then we're going to square it. 1/2 squared is 1/2 times 1/2, which is 1/4. So a 1/4 goes here. Now here's where it gets a little tricky. Did we add 1/4 to this side of the equal sign? No. There is a -1 out in front of this whole parentheses here. We really added -1/4 to this entire side because it's -1 times this 1/4. So since we added -1/4 to this side of the equal sign, we have to add -1/4 to this side, which I will just write as -1/4, since I don't like writing plus negatives. So -1/4. There we go. All right, we have now created a perfect square trinomial in here. That needs to factor. What are two numbers that multiply to 1/4 that add up to 1? Well, 1/2 and 1/2. That's the number we used. So this is going to look like x plus 1/2 quantity squared. We still have everything else to bring down. So we have f of x minus 1/4 equals -1, and then that, and then plus 6. The last thing that we need to do is solve for f of x, so I'm going to add 1/4 to both sides. All right, quick in our heads, 6 is really 24 over 4, plus 1 over 4 is 25 over 4. So we're left with f of x equals -1, x plus 1/2 quantity squared plus 25/4. Here's my disclaimer on this problem. If you felt good on example 1 and understood it well, that is awesome. If you were slightly confused on example 2, that is okay. As long as you understood example 1 well and could do something like that, that's great. I do just want to say that the only difference in example 2 is that we had a negative out front, and we do need to have a positive x squared in order to proceed. That's all. That was the only difference. It does get a little confusing with that, so if that confused you a bit, that's totally fine. If you understood example 1, you're good to go. All right, I saved the easier problems for last. This time we're going to convert from the vertex form to general form. Remember, general form looks like this. ax squared plus bx plus c. No parentheses. And so we really just want to multiply it all out. You do need to be careful about PEMDAS though, your order of operations. All right, so what I'm going to do first, I don't really have like rules to write off to the side here because it's just like multiplying some stuff. So the first thing we're going to do is multiply out that x minus 3 times x minus 3. And when we multiply x minus 3 times x minus 3, we'll get x squared minus 6x plus 9. And then we still have a plus 5. Quick little thing here to multiply a binomial by itself real quick to square it. Square this, multiply them together. So -3x, and then double it. So again, square the first term, square the last term. Multiply the two terms together and double it. All right, let's keep going. I don't want any parentheses in our final answer, so now we can distribute the 2 through. So we'll get 2x squared minus 12x plus 18, and then plus 5. No parentheses are are no longer needed because we distributed the 2. And then 18 and 5 is 23. Cool. So we have the exact same quadratic function, once written in vertex form, once written in general form. Here's our last example, converting again from vertex to general. We're just going to multiply it out. The first thing we need to do is square this binomial. This is just a -1. We'll distribute that at the very end. So let's multiply this out. We can use that little trick we just learned. Square this right at first, square this right at last. Multiply these two together, 2x, double it, 4x. That's just a quick way of foiling and not having to write it all out. It's pretty cool. All right, then we're going to distribute that negative through, so it's -x squared minus 4x minus 4, and that is our quadratic function going from vertex form to general form.